Now is the time at the end of our thermodynamics unit to talk about the concept of entropy. Entropy is perhaps the only concept we've encountered that's entirely new to most of you, I think. We've seen energy, we've seen heat, we've seen work before, but entropy is a kind of new formulation. Before I tell you what entropy is mathematically and how it fits in here, I want to describe what it is verbally for you. There's a bunch of different ways to define entropy. It turns out to be one of those really important concepts that is surprisingly difficult to define adequately. I mean, it's not as bad as the word time, but it's up there. The usual ways of phrasing entropy is that it's a measure of the disorder of a system. And that's actually not a bad definition, I think. I disagree with Dr. Smalley in that respect. She really dislikes that definition. It's a very civil, cordial, collegial disagreement, however. The better way to think about entropy, I think, though, in the end, the more profitable way, is to think about it as a measure of what you do not know about a system. If I make a system, maybe it's a box, and I've filled it with some kind of, gas, there's some macroscopic variables that I can know about this box. Macroscopic means big things. Big things like the temperature, the volume, the pressure, okay? I can have a pretty good idea what the composition is. It's this much nitrogen and this much oxygen and this much water vapor, for example. But that's most of the macroscopic state variables I can think of off the top of my head, to be honest with you. Number of moles, or number of molecules, I suppose. But it's not really knowing everything about that box of gas. Really, to know everything about this box of gas, I would need to know where each and every single particle in the box is at every single moment, and I would need to know where each and every one of the little buggers is going at every single moment. Okay. Now, in theory, if I ever knew where all of them were and where they were all going with infinite precision, I could tell you where they're going to be for all of time, but be that as may be. Thing is, I don't need to know what all those particles are individually doing to know what's going on for most purposes. For most of your life, you've encountered things like temperature, volume, and pressure, and that's been enough to really describe the gas. But if you really wanted to know what was going on, and really wanted to have high prediction capabilities, you'd need to know all the extra stuff. These things, all these little details, are called microscopic variables, or microstates, and these are the macrostates. Now, there are a lot of microstates, a lot of combinations of these particle velocities and positions that could lead to the same macrostate. I could shuffle the velocities around, because the velocities are all distributed randomly. There's some that are going faster and some slower, even if it's all the same element, or all the same molecule of gas. I could distribute them randomly and shuffle which particles are specifically going which speeds, and to still get the same temperature, volume, pressure, and number of molecules. I mean, even if we had some way of labeling the different elements, could still be the case. I wouldn't be able to tell until I looked microscopically and saw that it was maybe all the nitrogen that had one property and the oxygen that had some other property. So entropy is how many possible ways you have of combining these microstates, that is, all the positions and velocities of all of these particles, to give you the same macrostate. Okay? The more possible combinations here, the more, for a given set of these, the larger the entropy is. Okay? So, in a sense, if I just tell you this, entropy is a measure of how much I don't actually know about what each individual atom is doing. Now, this is interesting because knowing which each atom is doing really does set, ultimately, what's really going on. I mean, there are certain weird probabilities, for example. It is possible, for instance, at some time, for all the molecules to end up only on one side of the gas, or the box, and the other side to be a perfect vacuum. There's nothing in the laws of physics that said that can't happen. Now, statistically, you and I both know that's almost infinitely unlikely, that 10 to the 23rd molecules should each randomly choosing a side, 50-50, would choose the same half. Okay? And that's kind of what the second law of thermodynamics says. The second law of thermodynamics says that entropy, which we will denote by S, always increases or at worst stays the same. Well, at best, I guess, stays the same. So delta S is greater than or equal to 0. What that means is things want to go to find the most possible states for a given macro state. Okay? Moving everybody to one side of the box is actually just compressed where everybody is, and so you have a much better idea where all the particles are now, which means you've actually decreased the entropy. This law is really statistical. It just says statistically this does not happen. And with the size of the universe, the number of particles you have in a given system, that's bound to be the case. Now, let me give you the mathematical definition of entropy quickly. The mathematical definition of entropy, or at least the change of entropy, is the heat flow over the temperature. Okay? This could be in or out. Okay? It's positive in, negative out. So if I take some heat out of a hot reservoir and put it into a cold reservoir, the hot reservoir has a change in entropy that's minus Q over T hot. Okay? Minus Q because the heat's leaving. And the cold reservoir has a change of entropy of plus Q over T cold. Now, which of these two is bigger? The answer is, oh, okay, this one's got a negative sign, but ignoring that, this one is, because the denominator is smaller. That means that as heat spontaneously flows from hot to cold, there's more entropy gained by the cold reservoir than lost by the hot reservoir. So in the net, the change in entropy of the whole system is greater than 0. This is the second version of the law of thermodynamics, or it relates to the second law of version of the second law of thermodynamics, which is that heat flow only spontaneously goes from hot to cold. That's because that's the only way you could have the entropy change overall be positive. Okay? All right. I'm going to leave it off there because it's getting ready to be a long video. I will see everybody on Friday.